Click the bell icon to get latest videos from Ekeeda.
Hello guys, in this particular video we will learn the numerical analysis, the mathematical aspect of the low frequency response of CECE multistage amplifier. As far as low frequency response is concerned, we will deal with the problem number 2. In this particular problem we will have to find out the mid frequency voltage gain, that is nothing but the voltage gain that we'll be getting in your AC analysis, and the second thing is you have to find out the lower cutoff frequency, that is FL. Okay. Let's come to this particular circuit that we have on this particular screen. In this particular circuit, the Q1 is nothing but the stage 1 amplifier, Q2 comprises of stage 2 amplifier. Stage 1 is connected with stage 2 with the RC coupled, where CC2 is 1 microfarad each, and if you look at this particular circuit, stage 1 is identical to stage number 2. So I can say that R1, R2, R3 and R4, the values are same, right? RC1 and RC2, the values are same, that is 2.2 kilo ohm. RE1 and RE2 values are same, that is 1 kilo ohm. So I can say that if we go for the determination in the DC analysis, the values will be same. So you are reducing your mathematical work over there. Instead of calculating for stage 1 as well as stage 2, we'll just calculate the DC analysis for stage number 1. First of all, look at this particular numerical, what they ask us, what is given and what they ask us. Basically given is B1 and B2, that is beta 1 and beta 2 values are 200, both values are same. So here is also the one more advantageous factor for DC analysis calculation. And they ask us to find out the lower cutoff frequency and mid frequency voltage gain. Okay, so we have to go with 3 steps. First is DC analysis, calculate the value of the parameters which are important for the AC analysis voltage gain. Then we will move ahead for the exact AC analysis with AC equivalent model, and then we will move further for the calculation of low cutoff frequency. Okay, let's start with this particular DC analysis. Okay. In this DC analysis, we just have to look at the circuit which is for stage 1 as well as stage number 2. So for both these values, we will be getting the same values of ICQ, IBQ, VCEQ and whatever required parameters we want for AC analysis. Okay, so first of all, my aim is to simplify this circuit into Thevenin's equivalent form, because this is a voltage divider bias. Our first step for the DC analysis with voltage divider bias is your calculation of RTH and VTH. So once we say RTH is nothing but R1 parallel R2, that value comes out to be 3.58 kilo ohm. Your value of VTH is nothing but R2 divided by R2 plus R1 multiplied by the total voltage of the DC, that is 20 volts, and this is achieved by VDR, that is voltage divider rule, and value of VTH comes out to be 4.77 volts. So with the values of VTH and RTH, we will convert this complete complex circuit into your Thevenin's equivalent circuit, where we can say that this is your 2.2k, this is 20k, this completely your load I'm attaching with your simplified version of the resistance and voltage in the form of Thevenin's equivalent voltage and Thevenin's equivalent resistance. This emitter is connected to ground, and this forms your equivalent circuit in the form of Thevenin's equivalent circuit for the particular each and every stage of given numerical. As far as this DC Thevenin's equivalent circuit is concerned, we have to move ahead for the calculation of IBQ, ICQ and the further required parameters for the AC analysis voltage gain. Okay, so the required parameters are nothing but the value of GM, that is transconductance, and as I know that the value of GM depends on the value of RE, and further RE it depends on the value of the emitter current. So we have to find out first IBQ, ICQ and then IEQ, and further we stop the DC analysis, move ahead for the parameters of AC analysis. Let's see this. Once I say that I'll apply the value apply KVL for the finding of the value of IB, the DC value of IB, VTH minus VBE divided by RTH plus 1 plus beta times RE. That is nothing but my formula for your IB. Once I put the value, get the answer, just put the value, get the answer, pause your screen, just see to it that you are getting the correct answer for this particular IBQ. I have got the value 19.89 microampere, so IBQ is equal to 19.89 microampere. Beta value is given. I know the relation between IC and IB, so ICQ is equal to beta times IBQ. So we'll be just writing this value multiplication with 200, that's a value of beta. So ICQ comes out to be 3.98 milliampere. Just check your calc is working or not, right? And then come to me with the particular value of ICQ and IBQ. Now once I get the value of ICQ and IBQ, we'll just have to stop for the DC analysis. Okay, so we don't have to calculate the value of VCEQ because that is not the question in our numerical. Okay, so once we get the value of ICQ and the beta value is very high, I can say that once beta value is very high, I can also say that ECQ is equal to IEQ. Okay, because once beta is very high, as beta tending towards infinity, alpha tending towards 1. Okay, I can say RE, that is nothing but the parameter for your RE model. RE is equal to thermal voltage divided by IEQ. Thermal voltage is always we'll have to take the value of 26 millivolts. So 26 millivolts divided by whatever value you have got in the ICQ, just put that value and you will get the value of RE, right? Why we required RE? Because we require the voltage gain. Voltage gain depends on the value of GM, GM depends on the value of RE, RE depends on the value of IE, and that's what we are tending towards the calculation of the DC analysis. Okay, so DC analysis is finished. We have got the value of RE as 6.53 ohm. Inverse of that RE is nothing but the transconductance, RE is nothing but the resistance, and GM is nothing but the conductance. So we'll say that GM is equal to 1 upon RE. GM is equal to 0.153 mho. This calculation is only for the first stage, but I know that stage 1 and stage 2 are identical to each other. I can say GM1 is equal to GM2 is equal to 0.153 Siemens or your mho. Okay, so this is how we have finished the DC analysis. Let's move to one step ahead to go for AC analysis, voltage gain, that is mid frequency voltage gain. Okay, so let us move towards the mid frequency voltage gain. When we are going for the AC analysis, we have to keep this in mind that we have to short all the coupling and bypass capacitors, and moreover you have to short all the DC sources, right? So all the DC sources are connected to ground. So this is how, once I say this is the picture, I can say that this is how we will be getting the AC equivalent circuit, whereas R-Pi1, GM1, V-Pi1, this connection is for the BJT at the first stage. This R-Pi2, GM2, V-Pi2, this connection connected with ground of your emitter 2, that gives you the BJT equivalent, AC equivalent for stage number 2, and the respective resistances I just have to place according to your circuit given. Okay, now as far as this AC equivalent circuit is concerned, I just have to find out the value of voltage gain. As I know that AV1 multiplied by AV2 is equal to AV, we want to find out the value of AV. So let's move ahead to the value calculation of value of AV1. Right, so AV1, what is AV1? AV1 is nothing but minus of GM1 multiplied by all the resistances after the first stage, at the output of the first stage, that will be your RC1 in parallel with RB1 in parallel with R-Pi2. Okay, similarly I can say that the value of AV2 is equal to minus of GM2 into RC2. Because load resistance is not given, I'll just write the value RC2. Once we say that the product of AV1 and AV2, that product will give me the value of AV. Okay, so stay tuned for that. Calculate the value of AV1 and AV2, check your calc is working or not, and then come to me immediately with the values of AV1 and AV2 and check whether I'm correct or not, right? Okay, your values should be AV1 is equal to minus 102.03 and AV2 is equal to minus 336.6. okay, as gain has no unit, so we'll keep this values as it is and we'll just multiply these two values. You will be getting the mid frequency voltage gain. So your mid frequency voltage gain, that value will become AV is equal to 336.6 multiplied by 102.03. So just calculate these values. This is a huge amount of voltage gain that we will be getting. So ultimate answer for first finding is nothing but your voltage gain is of the value 34343.2. okay, now let us move to your step number 3, that is the low cutoff frequency. So step number 3, low cutoff frequency. Now for low cutoff frequency, we just have to deal with each and every RC circuit. okay, so here we will say that in this particular numerical we have total 5 number of capacitors. See to it that in this particular problem we have 1, 2, 3, 4 and 5 number of capacitors, so 5 number of RC circuits we will be getting. We have learned that how to deal with the 5 RC circuit and how to calculate each and every low cutoff frequency. So we'll move on to finding the value of the low cutoff frequency for each RC circuits, right? So one by one we will do. First RC circuit will be getting at the input stage, that with your RB1 and of course one resistance, that is R pi 1. So RB1 in parallel with R pi 1, the signal resistance is not there, so this CC1 and this particular RC circuit will give me the value of low cutoff frequency, that is FL1 is equal to 1 upon 2 pi RC, where R is equal to, I can say that it's nothing but RB1 parallel R pi 1. Calculates the value of RB1 parallel R pi 1. RB1 is around 3.58 kilo ohm. Let me check. Yes, so this value is 3.58 kilo ohm and R pi is nothing but the beta multiplied by Re, where Re is equal to 6.53. So here we will say that the R pi 1 comes out to be 6.53 multiplied by 200, that's the value of beta, 1.3 K. So 1.3 kilo ohm. Okay, so calculate this parallel combination and that will give you the value of R required for the FL1. Similarly, the value of CC1 that is nothing but given as 1 microfarad. Okay, now put the values of R and C and come to me, right? Pause your screen, calculate the value of FL1, again come to me. So value comes out to be FL1 is 166.89 hertz, right? So we can say that this is your equation number 1. okay, so similarly we have to move ahead for, let's say this is part A for FL1, and then we'll move ahead for the B part, that is for FL2. okay, we'll draw that circuit for B part. B part is nothing but for bypass capacitor. So here we will say this is your circuit for bypass capacitor and RC network, which comprises of RB1, R pi 1 and RE1. okay, we know the values of this. No, this is your CE1, that's of 20 microfarad, right? R pi 1, RE1 values are known to me. We'll just put the values in your fundamental formula of frequency, that is 1 upon 2 pi RC. What's the value of R? R is nothing but Re dash, whereas Re dash is equal to, I can say that it's nothing but Re1 in parallel combination with RB1 plus R pi 1 divide by 1 plus beta, or you can say beta as beta is much greater than 100. It's a 200, so difference between 200 and 201 is nil. So I can say either you can write 200 divide by 200 or divide by 201, one of the same thing, right? So take the calculation of this and then come again with me with my calculation and check your calc is working or not, right? Okay, this value comes out to be very less, that is around 24 hertz. Not hertz, it's 24 ohm. So 24 ohm multiplied by the value of the CE1, C is equal to CE1, that is of 20 microfarad. So just multiply these values with 2 pi and take the inverse, will get the value of FL2. You'll be getting 331 hertz. That's a value of FL2, 331.57 hertz. So this is the second finding we have got for the low cutoff frequency for second RC network. Let's move to the third RC network. We'll do this fatafat calculation. So third circuit is of in between first stage and second stage. First stage is RC1, second stage comprises of RB2 and R pi 2, this is CC2, all are connected to ground, and from this particular RC network we'll get the value of R and C as R is equal to the parallel combination of series combination of RC1 with parallel combination of RB2 and R pi 2. Okay, so we will say this value of R is equal to, I can say, RC1 plus RB2 in parallel with R pi 2. Mind well, if we don't have the bypass capacitor after this for second stage, we have to incorporate that RE2 with shifted resistance towards the base side. Okay, so right now we have the bypass capacitor, so we'll not take that RE2 into picture of this particular RC network. So calculate this value of R, calculate this value of C, put the value of R and C in this particular FL3, calculate the value of FL3 and then come to me, fatafat. Here we will be getting the value FL3 as 50.52 hertz. This is the third finding we have got from the C part. Okay, so the first finding FL1, FL2 and FL3 is finished. Let's move towards the fourth finding. So this is your CE2, this is your RE2, this is R pi 2, this is resistance RB2, and this is another resistance which is nothing but the load resistance for the second stage. First stage, I guess this is how we'll get the RC network. And FL4 is equal to 1 upon 2 pi RC. R is equal to, R is nothing but RE2 dash, RE dash I can say. Here RE dash, for this RE dash is equal to what? RE dash is equal to RB2 parallel with RC1, right? And that combination is in series with R pi 2. That complete series combination we have to shift it towards the emitter side, so we have to divide it by 1 plus beta, and then that combination is in parallel with RE2. So it's a big calculation, RE2 in parallel with the whole thing, that is nothing but RB2 in parallel with RC1 and then plus R pi 2 whole combination divide by 1 plus beta, and then we have to take the parallel combination with RE2. So the answer of this resistance is 13 ohm. So very less valued resistance, 13 ohm, and C is equal to CE2, which is nothing but given as 20 microfarad. So all these values of capacitances are given, so just have to find out the value of FL4 by putting these values of C and R in this particular formula. So we'll be getting the value of FL4 as 606.28. So 606.28 hertz. That's a very high value, right? So FL4 is equal to 606.28 hertz. So fourth value we have got up till now, and then we will move towards the last finding, that is from the output stage of second stage, right? So we'll draw this circuit. Circuit is comprises of CC3 along with the resistance RC2 only. So we don't have another resistances into picture, so it's a simple RC network, simplest RC network I can say. And your fundamental formula of frequency FL5 is equal to 1 upon 2 pi RC. R is equal to RC2, that is equal to 2.2k, and C is equal to CC3, that is 1 microfarad. Just calculate this value and get the answer of FL5. So value is 72.34 hertz. So FL5 is equal to 72.34 hertz. So far we have discussed all the values of frequencies for each and every RC circuit. Now the time has came to decide which particular frequency we have to take it as low cutoff frequency for my entire circuit. So as I know that the FL is nothing but the maximum value out of all FL1, FL2, FL3, FL4, FL5, we have to decide what particular frequency I have to take. So just write the particular values and then we'll decide which particular value we'll have to take. So first value we have got, that is 166 hertz. Then we have got the another value as 331 hertz. 331 hertz. I'm just approximating it, I'm not taking the decimal points. And FL3 we have got as 50 hertz. FL4 we have got, that is 606 hertz, and FL5 here we have got, that is 72 hertz. Okay, now out of these 5 values we have to choose the maximum value. So higher value is 606 hertz, so we can say that your FL is equal to 606 hertz, that is for entire circuit, and my answer is low cutoff frequency is nothing but 606 hertz for the given numerical. So far in the numerical we have found out with the DC analysis RE, then we move to the AC analysis. We found out the value of the voltage gain, that comes out to be 34342 point something, and then we reach to the value of the low cutoff frequency, that is nothing but FL is equal to 606 hertz. So we have finished this particular problem entirely to calculate the values of voltage gain and low cutoff frequency. So thank you very much for watching this particular video. Learn more and more ADC along with me, along with Ekeeda videos. Thank you so much.